Alright, so now that we have found the x and y coordinates of our intersections, now we still have to calculate the center line of the tool as the tool positions itself for the next piece of geometry that is now at an angle. So the first thing I want to point out is when we turn the corner at a 90-degree angle, we know that these two distances are half the diameter of the tool. Okay, but what I want you to notice is from the intersection point to the center of the tool, it takes that 90-degree angle that we're turning and cuts it in half. So that works the same on any intersection where you're getting ready to do an angle. When we come to this 20-degree piece of geometry, we have an angle right here and here of 20 degrees. But to find the additional move the tool has to make to be in line with the next piece of geometry, we cut that angle in half. So this leg and this leg will be 10 degrees. Okay? Let's take a look at this one here. So we have to go beyond this intersection to get ready to be in line with the next piece of geometry. And so instead of this being a 90, this leg is at 20, so there's only 70 left, right? So let me pull that up. The total angle from here to here, and notice these two legs are perpendicular to the tool paths. That's how I come up with that 70 degrees. Yeah. So again, from the intersection that we're turning about to the center line of the tool is cutting that 70 degrees in half. Okay, so again, that's 35 degrees. So we have two pieces of information to calculate this leg based on this angle being 35 degrees and this leg being half the diameter of the tool. So that's two pieces of information to be able to calculate this opposite leg of the triangle. All right, let's take a look at one more. Again, what you do is you draw a perpendicular line to the tool path, connect it to the intersection, okay, and then from here again to the next tool path. That now gives you an angle of 45 degrees. This is not a 90, but 90 plus 45, so that leaves 45. So again, this leg is splitting that 45 in half. Okay, right there, 22.5. So we know this leg, which is half the diameter of the tool. We know that the angle is 22.5. So now we know how to calculate this opposite leg. Okay, and the same for this corner. We still have a 45 degree included angle right here. So here's our triangle. We know this distance, we know the angle, so therefore we can calculate this distance. So that is how we would find the center line of the tool coordinate at the time that we turn at an intersection. Now I know that gets kind of complicated, but those will be the dimensions that you see in the program if the program was posted out by a software where it automatically calculates that little additional move where the tool is ready to be in line with the next piece of geometry that it's going to cut. Okay, so if you were to handwrite a program for this, let me give you a solution that will make your life simpler. Alright, so far we've learned how to offset our tool to create a tool path. And the reason I showed you that and taught you to calculate the endpoints based on the center line of the tool, offset half the distance of the diameter of the tool, is because that is the geometry that you're going to see in programs that you walk up to in the control that have been posted out by CAD software. Okay, you need to be able to see why that is offset like that. Now, if you're going to be handwriting a program on the machine for a part that has angles like this, it is really a lot of work to calculate those endpoints, at an angle. And I'm going to show you what you can do to not have to calculate those points, but use the actual geometry of the part and the coordinates of each intersection based on the dimensions of the print. Okay, so the toolpath that you write would actually look like this. We would actually write the toolpath as if the center line of the tool was following the actual dimensions of the part. So we would still have to calculate some of the endpoints because not all the information is given, but that's a whole lot easier than to calculate the angles and triangles of the offset toolpath. Okay, so the solution to this would be, if we had to actually handwrite this program, is write the program based on the center line of the tool following the actual geometry. And then what we would do is in the tool data offset page, we would add a 1/2 inch in the geometry column for the tool diameter offset, and the control would actually offset that tool path by half the diameter of that tool. Okay, does that make sense? So in order to activate that tool offset, you would have to, of course, add a G41 line left tool compensation. So it calls in that 1/2 inch diameter, and then the control will automatically offset it by 1/4 inch. So let's take a look at that tool diameter offset column on the tool data page, and I'll show you where to put that. So this is what the tool offset page looks like. Of course, you have your tool length geometry page or column, and then right next to it you should have a diameter with a geometry and wear column. Okay, now the wear is where you normally make your minor adjustments, either based on tool wear or to control the size of your part. So if you want to write a program where you use the actual contour of the part as your X and Y coordinates, then you're going to put the diameter of the tool right on this line right here, or whatever tool number it is that you're using. Okay, so obviously we're using tool number 1 here, so you would put 500 right there. All right, so what's nice about this is if you decide to change that to a 3/4 end mill, then that would just change to 0.750, or a 5/8, you would enter 0.625, and the control would automatically offset half that diameter and offset that toolpath by the correct distance. So very handy tool, especially for handwriting code.